So welcome to this session run by eSOL. My name is Rolland Dudemaine. I'm the Vice President Engineering for eSOL based in Paris. Today we're going to talk about how to take the best performance of today's and tomorrow's cores and ARM cores with our technology. First of all, a little introduction about eSOL. eSOL develops high performance and scalable software, and we help also our customers to improve their software in the wide embedded field and up to edge computing. One of the main products that we provide is a real-time operating system, and we have been selling and providing the solution for more than 35 years all around the world to the wide embedded industry, including automotive, industrial, medical, consumer, and the large embedded industry. The company was founded in 1975, and we have had since the beginning of the company a steady growth. Now we are present on the stock market, where we entered in 2018, and we have worldwide presence with some people, the headquarters based in Japan, but also some people in France, where actually I am, and in Germany as well. Let's move on to our main topic. When you look at the current challenges of the developing industry, one of the main topic is actually artificial intelligence. And when you look specifically at autonomous driving, you can see that some activities will take a lot of computing power to emulate what we see as an equivalent to our brain. A human brain performance for simple activities would take as an estimated around 10 teraflops, so 10 billions of floating point operations per second. But when you look at the full autonomous or equivalent to autonomous driving, full driving experience, or doing sports, for example, where the human body will be completely driven, and at the same time you have to manage all the inputs of what is around you. This is much more, and going up to 10 yottaflops, with only consuming around an estimated 20 watts of power, which is quite low. In comparison, when you look at embedded platforms, or even non-embedded, actually, something that is close to a medium range performance requirement is about 1 exaflop for the supercomputer Fugaku, for example, which is one of the most powerful platforms in the world. And this is using an amount of power that is incomparably bigger. You will not see a 30 megawatt system in your car anytime soon. If you want to go down to something that is more manageable, and again around 20 watts, it can be a tenth of the simplest performance for doing artificial intelligence for doing driving. So that means systems have to increase the performance requirements and reach a level of high performance computing that is even beyond what we have today at an efficiency level, even better. How do you achieve that? Well, you can try to make more efficient cores. And this is what ARM has been very strong at doing these days, in the past few years, past many years. But Moore's law tells us that there is actually a limit to the amount of performance increase that can be applied. At the same time, Mr. Dennard is telling us that there is a peak to the CPU frequency, and there's a technological plateau to that frequency. And indeed, since about 2006, the frequency of cores have not increased too much. And Mr. Pollack tells us that at the same time, even though that frequency is limited, the performance of a single CPU, of a single core inside the chip, is also limited. That means if you want to increase the performance of the overall system, well, you have to add more cores. And this is actually doable, technologically complex, but doable in the hardware side. But the software also has to adapt and improve to follow that trend. Another person that is actually very relevant here is Mr. Amdahl, who described that the performance of a particular system, parallel system, will only increase as much as there is a parallel part of an application of software. In the case of any algorithm, there is typically a part of the algorithm that must remain serialized, that must remain single threaded or single core to manage the inputs or the outputs, for example, and to coordinate all the parallel items. That means that the more you can make parallel, the more you can increase the overall system performance. But if you do not make that step of making the system more parallel, you end up with a platform that will be, by design, limited. This may be something that looks insignificant, but as cores are becoming higher count, this is really becoming visible. Now, this applies to every algorithm. This is true for computing algorithms, this is true for vision, this is true for video encoding, and so on. But this also applies to an operating system. Here, what we have is that the operating system is very often ignored in this entire computing estimation, but it is coordinating all the cores and all the threads and all the applications running on the platform, including the inputs and the outputs in every part of the system. So this operating system itself must also be parallel enough. Sadly, when you look at the current state of the operating systems, most SMP systems are actually following their history of historical single core to move up to multicore, and this introduced what we call a global lock. Depending on the operating system, you see this lock at a different level, sometimes at the application level or the system call level, sometimes at the very more fine-grained level, but there is really often a real lock that will be preventing other cores from accessing critical data at the same time. The reason is that inside the kernel of typical SMP OS, there is a single table of threads. So when you want to do communication between multiple threads, they have to be able to, the requester needs to be able to change the state of a particular thread for sending, if it needs to block, and also of the receiver, if it needs to unblock the receiver. To do that, it needs to access the global table, and then it has to wait for any other core that is currently accessing that global table. This is actually the place, the core place, where that Amdahl's law applies and the parallelism problem is becoming visible. Incidentally, that also means that there cannot be multiple transfers at the same time on fully independent cores. And that means that independent applications that are isolated on different cores with an SMP OS will not really be independent, because if they make requests to the operating system, they will be serialized with that global lock. In the past decade or so, there has been research work to define something called a multikernel, not to be confused with a microkernel. So you can call a multikernel a distributed microkernel, if you will, where the intention here and the design is that each core has a local table of threads. That means when you want to send a message from one thread to another on the same core, only that one core is affected and is taking its own kernel lock, if there is one. When you work intercore, then only the sender and the receiver core will be affected, but the other cores will remain completely unaffected because they are not concerned with the modification of these thread states at all. And again, the key here is that each thread table is local to the core. And that brings, from a performance level, it brings more parallelism. From a safety or security perspective, it brings more parallelism, and at the same time, a real freedom from interference, which is not present in typical SMP OS. So that might sound a bit anecdotic and really not visible from the application perspective. But in many SMP OS, actually, there is also a requirement to hold that table lock, that global table lock, to be able to just simply reschedule, because this will change the state of a thread. Here you can see on the slide a measurement where we compare an existing SMP OS and eMCOS, which is the multi-kernel designed by eSOL. And merely already, when you consider a system with 4 cores, which is the current system that can be deployed with 4 ARM A57 cores, the context switch time is almost double between what you can see for eMCOS, which is constant, and the total context switch core on the 4-core system with an SMP OS. So even without considering the API calls, the system calls to be able to optimize the system further, just looking at scheduling time, context switch time, the context switch time on any given core will be constant with the multi-kernel design of eMCOS, where it will actually increase on a typical SMP OS. So this is implementing real parallelism here and real concurrency. Because that distributed microkernel design or multi-kernel design is able to manage multiple cores in an independent way, that means it is actually also easier to make it scale. Scale to bigger cores, scale to multiple cores, or even to many core systems, like recent ARM designs for the HPC market with 96 A76 cores. eMCOS can run on this design without trouble and take advantage of the high parallelism that the platform brings. But it can also go down and run very well, already bring performance advantage on an homogeneous 4-core A57, A72, or current cores that you see on the market, and also is capable of scaling down to simpler ECUs where you have Cortex-R or Cortex-M systems for real-time and safety or IoT devices. It's actually quite interesting because eMCOS is also capable of doing the same message passing between cores that is happening on the inside a group of cores that we call a cluster, and also across groups of cores. So for example, the particular performance that you can see on the heterogeneous platform is going to be possible to take advantage on the 4 times big cores and the 2 times small cores. And your application will be possible to harmonize and run both on the big and the small cores with our real-time operating system. So hardware scalability is a strong point here. Another angle is software scalability. eMCOS, with its distributed microkernel, actually has a tiny footprint when you look at its core functionality of being able to do scheduling and to be able to do message passing between the cores to synchronize at the application level. But there is an expectation always to be able to use standard programming interface. So eMCOS supports actually two main ones. One is eMCOS AUTOSAR with the automotive AUTOSAR classic platform interface to be able to reuse classic platform applications. Or in the middle, a POSIX layer. The middle one can be used, for example, for computing workloads where you want to be able to run POSIX or Linux-like applications directly, but you don't want the overhead of the multiprocess system, and you don't want the overhead of the MMU context switch there. Then you can have a simple POSIX API that can be very useful for still doing high-performance computing, standard or classical applications. The most typical one is what you see as the multiprocess one, where it will be your more typical Linux-like environment, not exactly Linux, of course, but Linux-like, with multiple processes, PSE53 environment, and even the possibility to use a shell, to fork, exec, spawn, and so on. At the extreme right, you can see an extension of that eMCOS POSIX installation, where some operating system can be hosted on top of eMCOS POSIX as guest operating systems. We use, of course, the ARM-V extension to be able to host these guest operating system and the hardware acceleration wherever that is available. At the same time, that rightmost design is interesting because we can then host existing applications as a guest over in a restricted context in a VMM on top of the hypervisor next to real high-performance computing, which can take the full advantage of the eMCOS POSIX multi-kernel design and the full parallelism that that platform provides. So for legacy applications or applications that have not been ported yet, then it's possible to have a mix between real-time or high-performance application and existing middleware. Speaking of existing middleware, it's actually important to be able to reuse as much as software as you can. And in this context, on eMCOS POSIX, it is possible to reuse already several frameworks. Going from left to right, you can see adaptive platform, AUTOSAR adaptive platform. I already mentioned AUTOSAR classic platform for the smaller configurations, smaller ECUs. And now this is about the bigger platform. You can see also ROS, and in particular, eSOL was one of the founders of the AutoWare Foundation, which tries to apply the ROS robotic operating system framework to the automotive domain and transportation in general. And that includes ROS 1 and ROS 2, of course. So we're still very active in that domain. But it can be any other framework that you can run with a POSIX-compatible multiprocess operating system, whether that's Apache or Python or DDS frameworks with some open source or commercial partners. Well, you might have integrated and ported existing software and use it as it is, but at some point you need to be able to deploy new and specific applications to run them on a platform. Typical approach is that you will prototype on Linux on your PC and then want to deploy on the embedded target. And it's very useful to be able to reuse convenient and existing frameworks. So our current release already includes Eclipse support, and we're adding support for Visual Studio Code very soon, exactly to be able to follow that trend of reusing existing development tools, and even so for some open source development tools, or to be able to develop and debug your applications on embedded targets. So it is actually important to consider that the system will have to scale in hardware in the future. we are never seeing requirements in terms of CPU power going down, but only going up, with more power, more software to run on the same core, and more cores coming up on the system, up to many core systems and even multi-chip systems. eMCOS is well equipped to be able to run on these configurations. The software scalability itself is actually very important as well, so we can reuse a lot of the existing open source and commercial software by using standard programming APIs like POSIX and AUTOSAR. And this is actually important because it leads with that multi-kernel technology and the performance benefits it brings to a higher performance than average, and higher performance than what we see with our competition as well, and take the best advantage of the Cortex A, Cortex M, Cortex R, and even the server cores soon of the from ARM. Because of its core design, that also means that the footprint is very much optimized and that we can bring better determinism at the same time. This is the end of my presentation, so I thank you very much for listening. If there are any questions, we're available all around the world, so feel free to come to our website, or you can see our contact details on the slide here. Well, I want to then thank you for listening to this presentation, and I hope you will be able to contact us very soon. Thank you.